Welcome back to Mathsplained. As you guys can see, we have finally decided upon the name as well as the logo of our channel. A huge shout out to my friends who have helped me in both. A little heads up, all of the animation in this video has been done using the Manim library. Also, a huge thank you to all of you who have watched my first two videos. This channel was just an idea 2 weeks ago. Now it's a little growing corner for all of us curious nerds. And I'm genuinely grateful you're here. In the last two videos, we have looked at what is mathematics, and then we took a ride through the history of mathematics. We saw how mathematics didn't just drop from the heavens fully formed. It grew from questions and patterns and needs. 3000 BC to 600 BC, we met the Babylonians and the Egyptians. Arithmetic and geometry was introduced and was used for land measurement and trade. 600 BC to 300 BC, the Greeks became the pioneers of the mathematical world. Thales, Pythagoras, Euclid, and Archimedes were some of the stalwarts of this era. 300 BC to 1200 CE marked the era of Indians and the Chinese. Zero and the decimal system was introduced. Aryabhatta and Zhu Chongzi are two of the greatest mathematicians of this era. 800 CE to 1300 CE, we crossed over to the Islamic Golden Age with Al-Khwarizmi and watched algebra bloom. Then, during the 1300 CE to 1600 CE, the Europeans picked it up. It was the Renaissance, and several concepts, like the Fibonacci series, was found during this period. 1600 CE to 1800 CE was the beginning of modern mathematics as we know. Fermat, Descartes, Newton, Leibniz are some of the names. Calculus was introduced during this period. And then we finally reach the 19th century, a fascinating time for modern mathematics. One that we are going to talk about today. Somewhere in the late 1800s came a man who didn't invent a new tool. He questioned something we just all assumed was obvious. Georg Cantor, a man who made mathematical world so uncomfortable he was called everything from a fool to a heretic. Why? Because he dared to ask the question, can all infinites be the same? Now let that sink in for a moment. Infinity, the concept that means goes on forever, can have types. What does that even mean? Well, let's build up to that. In one of our earlier videos, we looked at two definitions of mathematics, a formal definition as well as an intuitive definition. In the intuitive definition, we have talked about mathematics as a language of patterns, and I want to stick to that. Yes, there are numbers and equations and formulas, but underneath all of it, patterns. Recognizing patterns, describing patterns, extending patterns, and sometimes breaking them. Let me show you these three simple examples of patterns. You've seen them before, but let's look at them with new eyes. First is an arithmetic pattern. The difference between the consecutive terms is a constant plus 2. Thus, we get a series 0, 2, 4, 6, 8, 10. This is called an arithmetic progression. These are the patterns you'll see in simple growth, like someone saving rupee 100 every month. Next up, we have the geometric pattern. For example, we start off with the number 1 and we constantly product it with 2. Therefore, we get 1, 2, 4, 8, and then 16, and so on and so forth. This is a geometric progression. You'll find this in compound interest, bacterial growth, or your folder getting duplicated again and again by accident. Next up, we have the Fibonacci sequence. This is a special pattern. Now, in this particular pattern, each term is a summation of the two terms before it. Here, 0 and 1 are the first two terms. The next one is a summation of 0 and 1. 2 is a summation of 1 and 1. 3 is a summation of 1 and 2. 5 is a summation of 2 and 3. 8 is a summation of 3 and 5. And finally, we have 13, which is a summation of 8 and 5. Now, this particular pattern is found everywhere around us. Pineapples, flower petals, seashells, spirals. Nature loves this particular pattern. All these patterns have something in common. They go on forever. They are infinite. Now, take a breath. Think about how often you've used the word infinite without really thinking about what it means. There are infinite stars, infinite scrolling on Instagram, infinite homework. But have you ever thought, is infinity a number? Can we measure it? All are infinites the same? Well, if I ask you to list all whole numbers, 1, 2, 3, 4, 5, you'd say, sure, that's infinite. But now, if I ask you to list all real numbers between 0 and 1, numbers like 0.1, 0.001, and so on and so forth, that's also infinite, right? But here's the real question. Are both infinites equal? This is where we take a leap, because infinity isn't just one thing. And the man who showed us that was Georg Cantor. Cantor didn't just study infinity, he organized it, he classified it, he showed that some infinities are bigger than others. And to do that, he built an entirely new branch of mathematics, a branch that we use so often these days, a branch of mathematics that we now know as set theory. You see, if numbers are the language of mathematics, then sets are the grammar. Sets help us group, compare, define, and reason. And for Cantor, sets became the way to understand the infinite. By the way, Cantor wasn't trying to be poetic. He was just working on trigonometric series. Yeah, the sine, cos, tan things that you've seen before. He wanted to know an answer to a very specific question. The question is, can a function be expressed in more than one way using trigonometric series? Now, if you cannot understand what is on the screen, no real worries. It's not relevant to our discussion. But this is what Cantor was working on. This is called a Fourier series. Now, to seek answer to that question, he needed to understand the real numbers between 0 and 1. Numbers like 0.1, 0.999, whatever. But wait, how many real numbers are there in an interval? How many real numbers can you count? Well, let's rewind a bit. We started with something much simpler, something much easier, the natural numbers. 1, 2, 3, 4, 5. Infinite, right? Sure. Now try even numbers. 2, 4, 6, 8, 10. Looks like fewer in number. But if we match each natural number to an even number like this, 1 to 2, 2 to 4, 3 to 6, 4 to 8, you see perfect pairing. Even though it feels like there are fewer even numbers that can be matched one to one with the naturals. This kind of matching is called a bijection, and that means they are the same size of infinity. Well, now Cantor said, let's go deeper. What about real numbers between 0 and 1? Can I list them all? Well, let's try. That brings us to Cantor's diagonal argument. Suppose I list all the real numbers between 0 and 1. Here I have taken arbitrarily random 10 numbers. For example, 0.123456789, then 0.234567891, 0.345678912, and so on and so forth. I've constantly just randomly generated 10 numbers. Now, what Cantor did is he said, let's take the first digit of the first number, second digit of the second number, third of the third, and so on, and flip each digit. Now, this number that we have found, it gives us a number that is very different from the numbers in the list, at least one digit, which means you can never list all real numbers. There will always be one more. Boom. There are infinites that are bigger than the others. And that brings us to uncountable infinity. Now, let's take a moment here. What are uncountable infinity? Basically, uncountable infinities are too vast to list, like real numbers, as we have seen. But there's also a countable infinity, which, by the way, Cantor gave the name Aleph null, and it is basically the size of the sets that can be paired with natural numbers. Now you'd think people would go, wow, revolutionary. Nope, people freaked out. Mathematicians said Cantor was destroying math. One even said he was a corrupter of his youth. His mentor, Kronecker, turned against him. Cantor suffered a lot, mentally, emotionally. But he didn't stop, because once you've seen infinity bent like that, you can't unsee it. So the next time you hear the word infinity, I want you to remember it's not some vague, unreachable concept. It's been thought about, tamed, classified by a man who refused to accept that infinity couldn't be understood. Well, let me leave you with something interesting. I call it the rupee paradox. Let's say I make a deal with you. In the first case, I give you 1 rupee and then I take it back. I give you 2 rupees, I take it back again. Rupee 3, take it back, and I do this forever. So at the end, what is it that you're getting? You get nothing, right? It's a pretty easy answer. But let's look at case 2. Now I'm doing the same thing, but instead I give you rupee 1, then rupee 2, then rupee 3, and I continue this forever. Then I start taking it back as well. But first rupee 1, then rupee 2, then rupee 3, and I do this still forever. Now, how much money do you have at the end? Is still the same answer? Is it still zero, nothing, infinite, undefined? Well, think about that. You had the same numbers, you had the same actions. It's just two different orders. And suddenly your answer flips. This, my friend, is the chaos of infinity. And this is the world Cantor dared to walk into. I think this is a good place to end today's video. Thank you to everybody who's sticked with me till now. In the next video, we will move into this new mathematical universe that we just set up. Not to do formulas, not to memorize definitions, but to understand the concepts and the principles behind this world Cantor had to set up. We will study set theory, a very integral part of your high school mathematics. Because once you've tamed infinity, you need new tools to describe it, and I'll try my best to provide you with these tools. Until then, keep playing with the impossible. Keep asking, but what if? And remember, math doesn't begin with a formula, it begins with a question.